So now the next speaker is Daniel, that will talk about the modeling of multi-messenger emission of various type of sources, starting with binary neutron star mergers.
Yes, okay, thank you. Okay, perfect. Yeah. Okay. Thank you very much. We'll try with this this microphone. I hope everyone can hear me well. Also in the back. Thank you. Okay, so this talk will be more from a theorist's perspective, from someone who does modeling of multi-messenger sources, compact object mergers, but also massive star collapse from a theoretical point of view, trying to model electromagnetic counterparts basically from first principles. So I was asked to talk about a kilonovae, and I apologize a little bit in advance that I'm actually going to widen the scope a little bit, because as I'll argue, a lot of these electromagnetic counterparts are actually connected in an intricate way. And so all of that information really has to come together and has to be considered together to really inform our understanding of a given event. So this is a sketch from 2016, so just before the GW170817 event happened, and it was sketched by theorists. And so down here you basically see the merger process. So you have the two neutron stars or neutron star black hole merging. So there's all these electromagnetic counterparts that were basically envisioned back then, and the story remarkably holds true, at least on the qualitative level, and even today. So we have basically precursor emission. We haven't really detected that yet, and I will also exclude that from the talk here. But there might be some pre-merger emission that we should be looking for in the future. And then Maria Grazia has already told us a lot about short GRBs and their afterglows. So there's a lot of non-thermal emission in the gamma rays and X-rays, even down to the radio. And then there's all these counterparts that we call thermal transients, so thermal counterparts, quasi-thermal black body emission that can come in different forms. So the most well-known one are obviously kilonovae, direct signatures of heavy element production in the universe. There can be variants of this, like a neutron precursor I will talk about in just a second. There could be jet, so talking about central engines of GRBs, there could be, and there will be interaction of jets with the environment, leading to thermal transients, to thermal breakout emission. I will also show in a second. So we have a really broad class of different electromagnetic counterparts, and I will try to walk you through some of these and show some sort of recent results from directly modeling them based on simulations, on first principle simulations. And the second thread of the talk, obviously underlying kilonova and why we're really interested in that from a more fundamental physics point of view, is the production of heavy elements in the universe. So that's a very long-standing question, at least 80 years or more. So the question being basically how the bottom rows of the periodic table are actually assembled in the universe. So it is still an open question, and we can discuss about this later on. It's really not just mergers. I'm 100% sure. There are other sources in the universe that produce these heavy elements. Roughly half of the elements heavier than iron. But sort of this will be a side thread of the talk. And I will apologize in advance also that I will even further widen the scope in the last couple of minutes to connect to Maria Grazia's talk and some of the talks that we'll hear later on by Matteo and others. I will also argue an intricate relation between mergers and other multi-messenger sources, such as massive star collapse. The reason being that these massive star collapse systems, or collapsars, and some extreme types of of core collapse supernovae that are magnetorotationally exploded by jets, and Matteo will talk about this. They can also synthesize heavy elements, and there's a lot of research going on, and they might actually lead to something that looks similar to a kilonova, in fact, and will accompany these events. So I will argue that there's an intricate relation between these different physical systems. And in fact, there's a range of different possibilities, and I'll end with some of these crossover events that we've recently detected that are really puzzling, and that really show that there's a lot of interesting physics going on. Okay, starting with neutron star mergers. So if we look for electromagnetic counterparts, we have to look for mass. We have to look how these systems actually eject material into space, because that is fundamentally the reason why electromagnetic radiation is being generated. And this has been basically studied with numerical simulations over the last 20 years or so, and we've learned a lot about how material can be ejected from these events. And what kind of radiation they produce, and we still learn a lot about mass ejection and the physical processes as we speak. So there's basically three main classes of how mergers can eject material into space. There's the so-called class of dynamical ejector, so material that is dynamically ejected, as the name says, as the objects collide. So two neutron stars, or a neutron star and a black hole. There are tidal forces at play that eject material into space, fairly cold neutron-rich material, but there's also so-called shock-heated dynamical ejector, so material that originates in the interface of the two neutron stars as they touch, as they collide, and heat up material to tens of MeV, very hot material, that then runs with high speeds into this sort of circumbinary environment. Later on, after merger, there can be strong winds from a remnant, from a neutron star remnant, driven by neutrinos and magnetic fields, so very complicated processes, and we still learn about the physics of this sort of fairly messy post-merger physics. So this is a channel acting then on tens to hundreds of milliseconds post-merger. And finally, a lot of this debris material from the merger will circularize around the final remnant, be it a black hole or a neutron star, form an accretion disk. And these accretion disks can unbind, as it turns out, a lot of material and drive winds into space that synthesize heavy elements and give rise to kilonova emission, and very strong kilonova emission. And I'm, in fact, going to argue that in the typical type of vanilla type events like GW17 or 817 perhaps, most of the kilonova actually comes from winds of these accretion disks. Now, as I said, a lot of this post-merger physics is still not well understood, and we'll hear more talks about dynamos and magnetic fields by Alexis in just a minute. So everything that I'm going to say is still to be taken with a grain of salt. We're still really just exploring the physics. But the interesting thing is that now, over the last couple of years, we've just put together basically for the first time all the necessary physics in a simulation to consistently try to simulate these systems and their electromagnetic emission. And I'll show you some exciting results from this. So the first thing is, let's talk about non-thermal emission, so radio to X-ray emission. Those originate from the dynamical ejector. So as I said, there's at the collision interface, material with high speeds are ejected into space. It typically follows a power law distribution in velocity space. And this has been now resolved by different groups with the latest versions of the codes and numerical improvements. And we really see very fast material running into space of 60, 70, 80% the speed of light or so. It's typically a tiny amount of mass, so just 10 to the minus 6 solar masses or so, but they run at 60, 70% the speed of light, so it has a lot of kinetic energy. And that becomes fairly luminous in terms of electromagnetic radiation. So it drives a shock wave into the ISM, in which electrons are accelerated and they start to radiate. We can now fully consistently model this in the simulations by solving the full Fokker-Planck equation of the electron and photon populations in these shocks. taking into account synchrotron, synchrotron cooling, inverse Compton cooling, synchrotron self-Compton, self-absorption, all the relevant sort of radiative processes. And we can come up with angular-dependent, observer-dependent emission predictions, also taking into account relativistic effects. And what we see here is, so here, for example, is one example for a system that is similar to GW170817, where we can nicely model the radio and X-ray light curves of this fast ejector. And it actually nicely fits some of the observations, some of the potential rebrightening of the short GRB afterglow that has been detected in the aftermath of GW17 or 17 on timescales of years now after the event. And there's still ongoing discussion as to whether or not we actually see the signature of this ejector running into space or not, and whether this is really a genuine a new component to the GRB afterglow or not. But this is just to make the point that basically based on simulations we fully control basically now these predictions. The other counterpart I wanted to mention is now moving to more thermal counterparts, is this early UV emission called neutron precursor. So this fast ejector is so fast that the free neutrons, so there's free neutrons and protons in this plasma, and it is so fast, in fact, that the neutrons don't find each other. And a lot of these neutrons cannot capture onto other nuclei to form heavier seeds. So these neutrons just end up decaying on their own free neutron decay time scale of 10 to 15 minutes. And that neutron decay reheats the plasma and generates quasi-thermal emission. And that's what we call a neutron precursor. And that's also now been observed for the first time fully self-consistently in numerical simulations. You can nicely see here the heating in the plasma of this high velocity tail that has the signature of free neutron decay on timescales of tens to 15s of minutes. And that's above the typical R process heating from the kilonova I'll talk about in a second. And also here we, for the first time, take relativistic effects into account, and sort of this relativistic Doppler boosting actually makes them a bit more brighter than we thought before. So that's good news for early UV follow-up in the future. We haven't seen any of this in GW170817 simply because, so here I'm showing you all these nice predictions compared to the observation. So we simply didn't get onto the event fast enough to see this, but this is certainly something we should be looking for in the future, because the neutron precursor, or also this this fast ejector, that will be a clear signature of a BNS event versus an NSBH event, for example. So that will clearly tell us the nature of the binary. Okay, moving on to the actual kilonovae. So what is actually a kilonova? Just because we're a fairly broad audience here, I will put in this one slide background here. So the basic idea really is that, as I talked about, we have like several mass ejection mechanisms. They eject material into space. This material will expand. The most important parameters that set the electromagnetic emission are basically three main parameters. That is the ejector mass, typically something of the order of percents of a solar mass. The velocity, which is ranges from a few percent to maybe tens of percent the speed of light. And the third important parameter is the composition. What we call the electron or proton fraction, which is the ratio basically of neutrons relative to all other baryons in the system. And that controls the nucleosynthesis. So that controls the production of heavy elements in the system, and therefore controls the opacity. So it turns out that if you produce very heavy elements, so going to the last two rows of the periodic table, lanthanides and actinides, they have opacities orders of magnitude higher than lighter R process elements. And so that really controls the color of the kilonova. And this R process, or this heavy nucleosynthesis, production of heavy elements in these events, occurs on a time scale of typically a second or so. I actually have a movie here, which actually does not run, so I apologize. So you have to imagine now, I wanted to show you a nice a movie of neutron capture and how this actually works, but the embedded movie apparently doesn't play. So anyways, so on a time scale of basically a second, these neutron capture reactions happen, and then on much longer time scales, the very heavy elements, the very exotic neutron-rich nuclei you produce, they decay by beta decay, mainly by beta decay. And that nuclear binding energy reheats the plasma and makes it glow, makes it a quasi-thermal radiator. And that radiation can come out of the expanding plasma once the diffusion time scale becomes comparable to the expansion time scale. And that's when we actually see the kilonova emission. That's typically on the order of days, for these typical parameters of like percent of a solar mass moving at 10% the speed of light or so. As I said, the nucleosynthesis is really key in predicting the nature of the kilonova, red versus blue. Lanthanides having much higher opacities, as I mentioned. So those high opacities move the transient into the sort of more redder bands or infrared, and on longer time scale, peak time scales of a week or so, compared to lighter R process elements. And in order to really predict this well, we need actually neutrino transport. So it turns out that neutrino emission and absorption in this plasma is key in setting the composition and therefore the opacity. So this is why on the modeling side, we care a lot about the numerics and physics of neutrino radiation transport in these environments. So I have to show this slide because Alexis is going to talk about this after me. So with all this complicated physics, we are now able to consistently evolve the post-merger phase and get into all this messy physics of generating kilonovae and also central engines of GRBs. So various groups have gone with more or less full sets of physics after this problem, and finding for the first time magnetic jets emanating from these post-merger environments. These post-merger environments are very complicated in terms of physics. So Alexis will talk more about this. So I'm just going to set the scene here real quick. There's various plasma instability. So there's Kelvin-Helmholtz instability. There's the magnetorotational instability in the post-merger remnant. There's magnetic winding. There's other sorts of turbulence that act as dynamos that generate and amplify magnetic fields and generate large-scale structure. And we can see them for the first time emanating from a merger remnant in this ordered jet-like fashion that has important implications for GRB central engines. So we see now for the first time jets actually plowing through. So here you see a post-merger system. Here we have a remnant neutron star at the center. Here's an accretion disk. You see this is all the dynamical ejecta that has been ejected into space, and a jet is now plowing through this environment. And this magnetic jet has already quite interesting physical properties. It has a magnetization of at least a few to 10. It has a Lorentz factor of at least 5 to 10. It actually wants to go higher, but we cannot simulate that for numerical reasons. But this is already getting very interesting and into the range of where short GRBs are. We get luminosities, Poynting fluxes, so luminosities of this jet of 10 to the 52 erg per second is also like in the ballpark of where you need to go. So for the first time, we are probably seeing here the emergence of a central engine for a short GRB, or maybe some subclass of short GRB, maybe sort of at the low luminosity end, perhaps maybe also just precursors of a short GRB. Or maybe at the very least, we see a jet forming that may see the black hole after this neutron star collapses to a black hole and then ignites an even stronger jet. So there's lots of interesting questions that we are now asking, and I think we're getting really close to really tackle this question of central engines from a more fundamental point of view. But and I think Alexis will talk more about sort of all this magnetic field generation and jet business. Now, coming back to the electromagnetic counterparts, so this jet breakout has also interesting implications because there's a lot of fast material that this jet ejects as it breaks out of the ejector cloud. and generates new an additional precursor signal to the kilonova, which is also in the UV and optical bands, happening on timescales of hours. So here's this neutron precursor I talked about earlier on hours timescale after merger. Then you have this sort of shock breakout from the jet on hours, and then comes the actual kilonova on later timescales. So let me talk about this real quick. Where do we think does most of the kilonova signal come from? Let's say in a vanilla type event similar to GW170817. Here I'm going to make the case that probably in many systems, in most systems, that is dominated by the accretion disk. So by the material that circularizes around the remnant. You can see here, this is the neutron star remnant at very early times after merger. It drives strong modes into the accretion disk, which then with turbulence, with magnetohydrodynamic turbulence, and again, Alexis will talk about this more, starts to generate strong winds from this accretion disk and unbinds a lot of materials, so a few percent of a solar mass or so for typical parameters. That is actually in very nice agreement with what we see in GW170817, for example. So this blue kilonova can be nicely sort of explained in this picture of strong accretion disk winds at early times that are irradiated by neutrinos from that remnant and are therefore completely blue, have very low opacity, completely lanthonide free. So this is a nucleosynthesis calculation. As you see, there's only light R process elements being produced. There's no heavy stuff, no lanthanides, no actinides, so low opacity material that nicely fits basically the observations. So I think now, several years after GW170817, we're coming to a more or less consistent picture, I would say, in which this blue emission may also come from an accretion disk in the post-merger phase. The red emission of GW170817 is something that was heavily discussed several years ago already, and for various reasons, mostly ejector velocity and ejector mass, I think were convincingly shown sort of also to originate from these post-merger accretion disks, at least in a system that's compatible with GW170817. But from the later stages, when the neutron star actually collapses to a black hole, and you have basically an accretion disk around the black hole. There's no strong irradiation by neutrinos at that point, and you can produce heavy elements all the way to lanthanides and actinides, so red transients, a red kilonova. Okay, in the interest of time, I will have to go fast now and just mention really briefly that there's a variant of these typical vanilla type kilonova scenarios, namely the scenario in which an indefinitely stable or very long-lived neutron star is being formed. So as the gravitational wave detectors will sort of sample more of the binary neutron star merger distribution, hopefully, as we move into the future and we see more events, we'll eventually also see the low total mass tail of the distribution. So there will be events in which a very long-lived or even definitely indefinitely stable neutron star will be produced, and in that case, the entire rotational energy, 10 to the 53 erg, that is stored in these objects, will be extracted, and it will be very difficult to hide that amount of energy. So, and that's really in contrast to the prompt collapse into a black hole, where you can hide all the energy in the black hole. But here, this energy has to go somewhere, and it has to go into the environment, and it will go into electromagnetic emission. And so one scenario that we envision here, and that's going back already quite a number of years, is basically the formation of a magnetar. So after a few Kelvin-Helmholtz cooling timescales of the star, the neutron star will have cooled down to temperatures where there's no neutrino radiation, there's no mass ejection anymore, and the magnetosphere will be set up. And you will form basically a magnetar that, very similar to supernova remnants, may in fact inflate a pulsar wind nebula, a very extreme version of a pulsar wind nebula behind basically the outgoing ejector. And that rotational energy, that 10 to the 53 erg that's extracted through the pulsar wind from this magnetar, will go into this nebula and will reheat and accelerate the ejecta, and will actually boost the kilonova, both in terms of overall luminosity, but also in terms of speed. And so this is what we call basically a magnetar-powered or magnetar-boosted kilonova. So these should be fairly bright events that we hope to detect, and would be very exciting observations, because we would directly witness basically the formation of a magnetar in these merger scenarios. Okay, and if I still have like two minutes left, hopefully, okay. Perfect, thank you. To connect back to Maria Grazia's talk and also to Matteo's talk later on, let me put all of this into the even bigger picture of other multi-messenger sources. So in this case, a massive star collapse. Maria Grazia has already talked about the fact that we think that long GRBs come from a different physical system, right? From different physical progenitors, namely collapsars. So the collapse of massive rotating stars that form an accretion disk, a black hole, and an accretion disk. Because of the angular momentum in the system that has to go somewhere, it has to go through an accretion disk. And we think those accretion disks power jets that give rise to long GRBs. So that's the classic story since the late 1990s. And in addition, we realized a few years ago that, in fact, these accretion disks might be very similar to what happens in neutron star mergers. And so the physical processes would directly translate to these systems as well, meaning that in these early phases, when the black hole has formed and the accretion disk has formed and the GRB jet is going off, the accretion rates are in fact high enough that the accretion flow can self-neutronize. So the accretion flow is dense enough for electrons to become degenerate. And in these degenerate conditions, basically so electron capture onto protons is favored over positron capture onto neutrons, meaning that basically you drive the accretion flow neutron rich, you generate an excess of neutrons relative to protons. And that is exactly the conditions you need to form heavy elements and therefore get something that looks like a kilonova, right? So far, so good. The interesting thing is that these GRBs happen, so the rates of long GRBs are less than mergers, we think, or comparable or less than that. But there's a lot more mass being accreted onto collapsars than mass accreted in neutron star mergers. So the total production of heavy elements could even overcompensate and could even be at least of the order of neutron star mergers or even more. The question is, how can we see that electromagnetically? Is there some way we can actually observe this and test this? And the basic idea is that in some of these collapsars, as Maria Grazia told us, right, there's a type 1b broadlined supernovae accompanied with a lot of GRB events, especially with low luminosity GRBs. And so in that case, you have some sort of successful supernova explosion, maybe from a brief proto-neutron star phase during collapse before you form the black hole. So you have some nickel-rich ejecta that powers the supernova light curve. And then later on, you have these disk winds coming from the black hole accretion disk, injecting high opacity material with lanthanides. And depending on the mixing and some physics we still need to explore, these can actually tremendously change the supernova light curves. So there's a whole range of not influencing the supernova at all to completely changing the nature of the transient. In sort of anything in between is possible. In general, there should be always at very late times a signature in the infrared coming from the lanthanide elements basically from this kilonova signal of heavy elements being formed. And there's first observational searches for this. First papers coming out. One spectacular one was this extraordinary bright GRB that happened recently, the brightest GRB of all times. We got some JWST data on that. We found a supernova, which was quite exciting in the infrared, but we didn't find any direct evidence for our process yet. And I can go at length into this of why I didn't expect our process in this event to happen in the first place, but maybe this is something for later on. So the point is we need to keep searching and looking for more long GRBs to see perhaps something like a kilonova signature at late times. Now, and I'll finish with this basically. Let me put this into the broader perspective, and this is kind of like a theorist's, a simple-minded theorist's sketch of how all of these things may actually connect together. So as I envisioned, there's a range of different central engines for multi-messenger sources, and they are all connected by the production of heavy elements and therefore by some sort of kilonova type signature. On the one hand, we have the mergers, so the binaries, that in some corner cases of the low total mass tail of the distribution may lead to the formation of stable neutron stars, as I mentioned. But we can also come from the other end, from the massive star collapse end, and go down in progenitor mass, coming from tens of solar masses here with ordinary collapsars and typical long GRBs, down to lower masses where we form neutron stars. And Matteo will talk about this. So we might have some magnetorotational driven explosions here from a neutron star, as opposed to a black hole central engine. And at the high end, we might have, there's also recent work by our group on even much more massive stars above the so-called pan-stability supernova mass gap that might actually behave similar to ordinary collapsars, and that might also lead to interesting electromagnetic transients that we can look for with LSST and especially with Roman once it's up. So this range of central engines, I think, also makes sense because we know there's also a diversity among the type 1c broadline supernovae, ranging basically over 2 orders of magnitude in energy and brightness. So sort of this perhaps there's a continuous transition between low luminosity GRBs and regular GRBs as we see them basically in the supernovae. And on the theoretical end, this would sort of correspond to this sort of continuous transition between magneta or say neutron star central engines to black hole central engines. So here we have basically, in addition, the 1C BLs, we have kilonovae here. I talked about this quite a bit. We think that short GRBs come from these systems. Perhaps with these long-lived neutron stars, we get some sort of extended emission, and maybe there's some classes of short GRBs with extended emission that come from these long-lived neutron star systems. And then on the massive star side, as I was arguing, we should see some sort of kilonova signature here, accompanied with the supernova signal. They might be very strong for these extremely massive progenitors, where there's most likely no supernova explosion accompanied with that, because it's very hard to explode the star in sort of a classical supernova picture. So perhaps these are just extremely massive kilonovae, which we call super kilonovae, in fact. So very red and very massive events that eject maybe up to solar masses of our process material. But they could also be associated with long GRBs. Now the picture becomes even more complicated, and this is really my very last comment. I'm sorry. So this is basically the range of central engines I sort of imagine. And now just over the last couple of years, we've seen these kind of crossover events, and Maria Grazia already mentioned these. So events that basically from the X-rays and gamma rays look like long GRBs, but then in fact are accompanied with classical kilonovae that look like GW17 or 17, and have other environmental circumstances that make them look like mergers, in fact. And so the question is really, what are these events? How do we interpret them theoretically? and what does it mean in terms of this continuum here, and how sort of connections sort of across these lines can be made. But I'll stop here, and maybe we can leave that for discussion later on. And I'm happy to take any questions. These are my conclusions. Thank you.
Daniel?
Thanks for this really interesting talk. The neutron precursor, UV, of course, we didn't see it for 1708-17 because it didn't have the right UV, the right part of the sky. And I guess in the future, that'll be better. There was also, have you looked in Galax 2003, 2013, wide-ish field of view, UV data that you might be able to, have you tried searching in Galax, for instance, for signs of a neutron precursor?
I haven't. I'm sorry. No.
Okay, maybe we should try.
But it's something one should do, yeah.
I might have misunderstood you, which will clear the confusion from my head. But anyway, so the other UV thing, this polaroidal outflow, which we did see in 1708-17, did I understand right that you're saying that in order to see that, the remnant still has to be a neutron star at the time that you see this outflow, or?
Great question. Thank you. So there's a separation of time and length scales in the problem, right? So the emission really just comes out. These thermal transients, they basically come out when the diffusion time scales of photons becomes comparable to the expansion time scale, and that's in this case of this jet breakout would be something of like hours or something after. Several hours after the event, and by that time, the neutron star will for sure have collapsed to a black hole. So those are basically disconnected. It's just really the material moving further out into space need to decompress, and so for the photons to be released.
So where I'm going with here, I'm just thinking how that impacts the X-rays, because I guess the diffusion timescale is a bit different. Is if you had a neutron star for a while that collapsed down to a black hole, I am assuming, I guess it's not necessarily the case, that neutron star would have been a magnetar, in which case I'd expect to see a bright X-ray component from the spin down at around the same time as the UV, which we didn't see. But would the X-rays significantly precede the UV then, if you had, or can you just not bother with it?
Yes, so they will basically come out fairly fast. So they will have to follow the flow. But like, let's assume that these X-rays go like that. This magnetic jet that I mentioned, that basically they come from similar GRB picture where they're generated interior to the jet, and then that material will actually escape at high Lorentz factors, and so there's only a slight delay relative to the light travel time.
Right, but I don't mean the jet. I mean the sort of isotropic. When you spin down a magnetar, you get this kind of isotropic X-ray emission as well.
Okay, so you're thinking about the magnetar,
Yes, I'm thinking with the magnetar. So if there's a neutron star for a while that's launched this UV poloidal component, when do we expect to see the X-rays from the magnetar spin down associated with that process? It's relative to the UV from the same thing, if you see what I mean.
Yeah, great question. Sorry, I didn't understand quite the scenario, but you're right. So if we assume that there's sort of a more or less stable magnetar forming in the event, then basically for that X-ray emission to emerge, we have to wait for a few Kelvin Hamil's cooling time scales. So for the magnetosphere to be set up, and then to extract actually the rotational energy, so that takes a few seconds. But after that, the X-ray emission could come out. So that would be fairly prompt.
So the fact that we saw this nice UV component but no X-rays at the time isn't a problem to you. That's expected.
No,
the X-rays would have been way earlier.
Yeah.
Damn. Okay, so we were too slow again. Okay.
Hi, thanks for the great talk. Coming back to kilonovae, I was curious to know what's the current status right now on the knowledge of the cross sections for all the heavy elements that are super unstable and very neutron heavy. I mean, as you know, it's a very important factor to know the light curves and also the rate that are the outputs of our process, nucleosynthesis. So I was just curious to know where we are now in the precision of the knowledge of that.
Excellent question. Thank you very much. This is actually a slide that I had in my talk, and I moved it out for time constraints and to cover the bigger picture. But you're pointing your finger into an important problem. So there's a very nice, there are very nice studies by now. So there's a very nice paper by Jenny Barnes et al. And others that look into this problem in great detail. And it turns out, depending on the nuclear physics you assume, and it's mostly in fact the mass models of heavy elements. So how the masses of these nuclei behave, because that controls the nuclear energy, so the binding energy that is then heating the kilonova. So depending on the mass models of heavy elements and the fission prescription, so how far you can go with a given neutron flux and how spontaneous fission and sets in, that actually tremendously changes the total heating rate of the plasma, and so the total amount of energy you have available and the timescales over which that's available. Long story short, the heating rate and the bolometric luminosity of the kilonova can basically vary by an order of magnitude, depending on the specific nuclear physics you assume. I think, in general, the situation is not that pessimistic, but